Hello. In this presentation, I'm going to go over some basic information about how C code is compiled into what we call object code or instructions. It might be a good idea for you to review the first ASM activity that we did earlier before break. Okay, so here's that code from that activity that was in a file called sum.c. Now, code like this, C code, gets, sorry, hang up. Just getting a pointer together here. All right, so code like this, a C program, can be compiled using these flags here, minus capital OG and minus capital S, to create simply an assembly language program. And that's what we're going to work with most of the time for the next few weeks of the semester. Now, you have been so far actually compiling your code all the way through to a binary executable program, which is sometimes called made of object code. So I'm going to talk a little bit about this. We're going to look at this a little bit, but then we're going to kind of ignore what this object code looks like because it's very difficult to decipher. And luckily we have this assembly code instead that's easier to read. So what we're going to do is we're going to start from the bottom here, the executable programs, and I'm going to go back up this compilation process and end up at assembly instructions that we'll just briefly get into, and then we'll start using in more detail in following presentations. Okay, so now here is how I went ahead and compiled the program called sum from sum.c. And so you see here that the GCC created this binary executable program called sum. And then on the next line here, you'll notice how then I executed sum. And when I ask that program to get executed, what happens is this binary executable form of the code gets placed in memory. And in addition to that, that's code. That's not, in this case, code means C. It means binary instructions, not C. And then over here, you see in the C program, we've defined some variables. Well, the places for those variables get assigned to what's called a data segment of our program in memory. And that then the data can be moved back and forth. The CPU sends addresses over to memory in order to get each instruction that's going to be executed one after another, and also in order to get data and have it sent back. All right, so once we have this executable, that came from something called a linker. So the linker takes object code, these executable instructions here. These are instructions that the machine can execute. You'll see they're 1, 3, or 5 bytes long. So here's one that's 1, here's one that's 3, here's one that's 5. They make no sense at all to us, right? They're very hard to interpret. So we're not going to look at these very much anymore. there are sets of instructions like this for all the various C libraries. And so the linker will put the C libraries, like ones for, say, printf, and put those together with the code from your C file that got made like this, and then create this final sum program. Now, some of these libraries can be what's called dynamically linked. So not all the code like this for printf will be put in, but a way to access that code on the fly when you're running the program is established. And that's called dynamic linking. And we do that a lot these days because programs will be really, really large if you brought in every library whose functions you may or may not use, and instead just bring in a function when you need it. Okay, so this is that object code. And then over here, these are addresses of where each of those instructions are located in the memory of the machine. Now, there's a program called a disassembler, which can take any executable that you have. That disassembler's name is objdump or object dump. And you put in your executable, and it spits out something like this. This is only part of it for our sum program, but it shows this particular function, sum store. Here's its the instructions again, and then here's the assembly that comes from it. So we call this a disassembled version of our code. And this can be handy when we want to take some executable and see if we can figure out what's inside of it. You do have to be careful, though. Anything can be disassembled. So here's an example of doing it on Microsoft Word. But you have to be careful because a lot of companies will actually forbid reverse engineering. So if you look really closely at the Microsoft end user license, you can't actually do this and try to figure out what their underlying code is like. Just an interesting little aside there. We're not going to use this disassembly too often in this class. We're primarily going to look directly at the assembly language. Okay, so here on the left we have our object code. We don't like this very much. It's very hard to read. This assembly version is much easier. Now, part of GCC is something called an assembler, which takes the assembly version of the program and creates this binary version of the code. And the assembly is nicer for us to study because it's textual and we can read it much more easily. All right, so now here is the assembly for the function sumStore in our program sum.c. So this is an example of how the compiler, if we give it this -S option, will create this assembly that looks like this. We also give it this -OG option because the assembly that gets created using this flag is easier to read. So the -O stands for optimization. And the compiler can get crazy and make some very fancy assembly code at higher levels of optimization that gets to be really hard to read. So we're going to be using this -OG because it's going to give us assembly code that's easier for us to interpret while we're first getting used to it. All right, so now let's look at a few of these different kinds of assembly instructions and realize what they are. So some assembly instructions perform arithmetic. We're going to look at quite a few of those in the next few presentations and in the activities. So here's one example. This is saying take what value is in register, a register called RSP. We'll learn about all these register names as well. And subtract 24 from it. And you'll see all sorts of other arithmetic operations that we can do. So we'll be studying a bunch of those. Another one that you're going to see a lot of is transferring data, because we need to take data from memory and put it into a register before we can operate on it, like you see here up in the subtract function. So there'll often be movement of data from memory into a register, and then storing that register data back into memory. And then also we do sometimes move data from register to register. And so these parentheses here are indicating that we're taking something from memory. So this is memory to a register. This second one here is from a register to memory. And then this third one is from one register to another. And we'll learn about all these register names in the next few presentations. Now, another thing that some of these functions do is do what we call transferring control. And the classic one of these is an operation called call. What this is saying is now go over to the code for a different function named plus and start running that code. And so this is how we go from one function to another at the assembly level. All right, so to kind of summarize all of this that I've just gone through, we can have C code that looks something like this. We're going to learn a lot about this star and pointer dereferencing. The idea here is that dest is a pointer, and we're going to get the place in memory where it is pointing to. And in this case, we're taking whatever is in variable t and putting it in memory where dest is pointing. And we'll get into this pointer dereferencing several times over the next few presentations. But you may want to familiarize yourself with this, because this is going to be something that we're going to do quite a bit of. Okay, so now this is the corresponding assembly statement for this particular C code statement. Now in this example, I've given one where there is a one-to-one correspondence. This doesn't always happen. There could be one C code statement that turns into many assembly statements. There also could be one assembly statement that takes care of multiple C code statements. So we're going to see this, and this is going to throw you for a loop for a while till you kind of get used to it. Now, in this case, what this thing is saying is take what's in register RAX and put it back into memory where RBX is pointing. Now, what this means is that dest must be in RBX and T must be in RAX. That's something that we're going to be able to start discerning as we compare C code like this to assembly code like that. So you'll see more examples of this kind of thing as it goes on. So in this case, we're saying let's take something that was in a register and put it back into memory at the register where RBX is pointing. And now the corresponding object code, which we are going to see really no more of for the rest of the semester looks something like this. And this, of course, gets much harder to decipher. You know, you just look at it, those numbers don't mean anything, right? But that is the instruction that's stored in memory and is being executed by the machine. Luckily, we're going to be able to look at this and not worry as much about these instructions. All right, so that's it for this presentation, and next we're just going to keep diving into more and more of this assembly code and the register names and things like that. So stay tuned for that.